An offset h must be introduced into a solid circular rod of diameter equal to d, knowing that the maximum stress after the offset, that is after the offset we have this figure, is introduced must not exceed 4 times the stress in the rod when it was a straight. Determine the largest offset that can be used. You have to find out the value of h. Originally, when the bar is straight, correspondingly we have stress sigma is equal to P divided by the circular area, that equal to pi by 4 d square. So we have P divided by pi divided by 4 will shift in numerator, so we have 4 times of P divided by d square. And now maximum bending stress will occur at this point, and here the distance between these two fiber, that is the centroidal of the horizontal and the centroidal of a offset, is the same distance that will be the distance of the top fiber when it's a horizontal position and the distance of the horizontal position here of the bend position. So this distance A to B, that is the distance of A to B, which one is the straight horizontal distance, is same as the distance between the two center lines. So this one is our offset, and this offset distance E is same as equal to h. Check here that this is a straight portion, and in the straight portion we have top fiber is A and the top fiber of the bend position is B, and we have given the distance between the top and top fiber of both the straight portion and the bend portion is equal to h. It means that the distance of the centroidal axis is also equal to h. So we have eccentricity equal to h. Let's call here this point is the C point and this point is a D point. At these 2 points here we have the maximum value of a stress, because we have a axial stress and we have a bending stress. So if we cut at this section, we can show here one internal reaction. This internal reaction will be exactly opposite and will have the same value that of P because of sigma fx. So this point here is our G point, that is the centroid point for the offset, and this force P above G will make a anti-clockwise moment, and therefore we have to show here a clockwise moment, and this value of the clockwise moment is the internal reaction, and this internal reaction is same as P multiplied by H. So this one is a hogging, therefore we have maximum tensile stress at the bottom, that is at point D, and we have maximum bending stress but compressive at point C. Anyhow, we are interested in the maximum value. So this time we have sigma maximum will be equal to axial stress is force F divided by area A plus bending stress will be same as equal to M multiplied by the top fiber, which one is equal to D by 2. We have diameter is D, so we have Y value is equal to D by 2 divided by I. The given condition is that this maximum stress will be equal to the 4 times when the bar is horizontal. This sigma value is same as P divided by A. The given condition is that the maximum stress should not exceed 4 times of original value of sigma when the bar is straight. It means that we have sigma max will be equal to 4 times of sigma equal to sigma plus we have M is same as P multiplied by H. Y value for circular cross section is D by 2, so we have D divided by 2 multiplied by moment of inertia is same as pi divided by 64, so 64 will shift in numerator, D to the power 4. We have 4 times of sigma and this sigma, so we are left here with 3 times of sigma is same as equal to 64 and 2 is 32, so we have 32 times P multiplied by H. One of the D will be get cancelled, and in denominator we have pi D cube. Sigma we can replace as 4 times of P by pi D square, so we have 3. Sigma is equal to 4 times of P divided by pi into D square. On the right hand side we have 32 times P divided by pi. Purposefully I write here D square, and one term of H by D is left, that is the extra term. What we observed here is that pi D square and pi D square will cancel, P and P will cancel. In that case we can calculate the largest offset H in terms of D. this 4 and 32, 8 is left. So we have 3 times of D is equal to 8 times of H. Or we can say offset H is equal to 3 by 8 times the diameter. That is equal to 0.375 times the diameter. Then the stress maximum at point D will be 4 times of the original stress. Knowing that the magnitude of the horizontal force P is 8 kilonewton, so this value of P is 8 kilonewton, we have to find out the stresses at point A and B. This time again the force P is not passing through the centroid of the given cross section. So to get your idea clear, we'll visualize from this side and we'll develop the FBD. So if you visualize from this side, we have shown the figure here. This point is top point is equal to A and we have bottom point equal to B. This total height here is equal to 24. So we have depth D will be equal to 24 and we have width, which one is perpendicular to the board, that will be equal to 30 mm. So in this case we have width B will be equal to 30 mm. So this one is representing the centroidal axis and the centroidal axis from A at a distance equal to 12 mm, as well as from B is also equal to 12 mm. So both this distance equal to 12 mm. The force P is exactly passing through the centroid of this rectangle and at a distance equal to 45 from the top edge. So this distance is same as equal to 45 and through this point the force is passing, and this force is a force P and the magnitude of this force is equal to 8 kilonewton. So this force is 8 kilonewton. So this one is representing the centroid of the section AB, and the centroid of the section AB from the line of action of force is at a vertical distance of 45 minus 12. So centroid and the line of action of force will represent here the eccentricity, and this total distance eccentricity is the distance between A and where the force is acting is 45. From this you have to subtract the 12. So 45 minus 12, that equal to 33 will be eccentricity. So we can cut here and we can show the internal reactions here. So let's make a cut near the section AB and we'll show the internal reaction. This force is acting to the left, so the internal force will be acting in a rightward direction. Let's say this force is equal to F, sigma Fx is 0, so P and F are one and same value, that equal to 8 kilonewton. And this force above G will make a clockwise moment, and if it is a make a clockwise moment, then you have to show here anti-clockwise moment. So this one is a anti-clockwise moment, and the anti-clockwise moment is M is equal to the force P multiplied by the eccentricity. This time we have force equal to 8 kilonewton and the eccentricity equal to 33 mm, and kilonewton we can multiply by 10 to the power 3. So this answer will be Newton mm. Because of the moment the bending stress will produce, and because of the force F, the compressive stress is produced. The compressive stress at A and B is equal and is negative in magnitude, because compressive you have to take as a negative value. And this one is representing the hogging. So for hogging you have to take the negative value of M. So in this case we have to take the negative value of M is minus 264 into 10 to the power 3. That will be Newton mm. And for point A here we have distance YA is positive is equal to plus 12, that will be mm. And for B, the YB distance below the centroid you have to take as a negative distance, that equal to minus 12 mm. Using YA, YB and the moment we have breadth equal to 30 and the depth equal to 24, we can calculate the bending stress at point A and the bending stress at point B. So we'll continue with this figure. We just want to analyze here what is the stress produced at point A and B due to the force and the moment M. So in this case the force F will produce the compressive stress, and the compressive stress will be equal to sigma C, will write here as a compressive stress is P divided by A. Since compressive will take it as a negative value, So in this case, the force P is same as equal to the force F. So we can write here minus F by A also. And this value is minus 8000. Cross section area is a rectangle here with a width is equal to 30, depth equal to 24. So we have width is equal to 30 and the depth equal to 24. Here area A is same as B multiplied by D. So this much megapascal will produce as a compressive stress and equal in magnitude for A and B. A is minus 11.11 megapascal. Is same for point A as well as B. A and B both are in compression. And the bending stress we can calculate. So for calculating the bending stress sigma B, we have minus M multiplied by Y divided by I. So let's calculate first I here because that is a common term. For rectangular section, I is equal to 1 by 12 multiplied by breadth multiplied by D cube. So we have 1 by 12. We have width is equal to 30 and the depth equal to 24, and we have to make a cube of it. Is 34560 mm to the power 4. Now we can calculate the bending stress here. For point A, you have to put the value of Ya is equal to plus 12 and I is equal to 34560. So we have bending stress at point A equal to minus M, and we have M is equal to minus value. So we have minus 264 into 10 to the power 3. M is minus because it's a hogging. Ya is equal to 12 and divided by I. And the moment of inertia is 34560. So this value is equal to is 91.66 megapascal. Now the point A here is a top fiber which will coming in tension. So for bottom fiber we have compressive stress and same magnitude because we have Ya is same as equal to Yb. So in this case Yb will be again equal to same answer. Only thing that the value of Y you have to take as a minus 12. So we have minus 264 into 10 to the power 3, and Y distance, since it is lying below the centroid, you have to take as a negative value, that is minus 12, divided by moment of inertia equal to 34560. So this value is minus and minus is plus and again minus is minus 91.66 megapascal. So individually we are knowing the stress at A and B, that is the axial and bending. So we can calculate the total stress at point A. That will be equal to sigma is sigma compressive, that is this value, plus bending stress at point A. We have compressive stress here is minus 11.11 and bending stress at point A is positive 91.66. So approximately this value come out to be 80.6. This is rough estimate. And the bending stress at point B is sigma is again equal to the compressive stress plus we have bending stress at point B. Compressive stress is same as 11.11. Bending stress at point B is equal to minus 91.66. So round up to this value is come out to be minus 102.8 megapascal. It means that the B is in compression and A is in tension. So there is a tensile stress at point A and the compressive stress at point B. A circular post and the rectangular post are shown in the figure. We have circular post of a diameter equal to D, and exactly on the tip we have one force is acting equal to P in a downward direction. Same is the magnitude of the force in the rectangular post. He says that the diameter of the circular post and the depth of the rectangular post, that is D and D, are one and same. The maximum tensile stress in both the posts will be the same when the width B, that is this width B of the rectangular post, is in terms of D. You have to answer your question. Now both the force P here will develop the compressive stress, and we want here the maximum tensile stress. It means that you have to select the value of bending stress as a positive value. If we select the value of the bending stress is positive and the compressive stress is negative, then the resultant stress may be a tensile stress. So for maximum tensile stress, that is value of sigma maximum, and we want tensile in nature. Here the stress due to P is a compressive stress, so that will be simply P by A. And the bending stress you have to select as a positive value. And the maximum value of a bending stress is given as M multiplied by C divided by I, that is the moment of inertia. And this value is same for circular post as well as for the rectangular post. So let's label here the circular post as a and the rectangular post as a B. So in this case, the circular post as a centroid is represented by G, where horizontal axis is represented by Z, and the vertical axis is represented by Y. This one is a standard procedure for us. And we have diameter equal to D, so the maximum stress will be at outer fiber. So as far as the moment of inertia of a circular section is considered, we have moment of inertia about y-axis here, because this one is the point P, and if we shift the force at point P, so if the force is shifted, it will be shifted here, that will be the value of P, and this force will make a moment about the y-axis. So this one is our y-axis and this one is our z-axis, and this force as the eccentricity equal to same as d by 2. So in this case the eccentricity will be equal to E is same as d by 2, and this force about point will make a clockwise moment, but that moment takes place about the y-axis. So it will develop a moment about the y-axis. So this one is moment M, and this moment is same as P multiplied by E. So you have to take the I value, and I value for circular section is same as pi by 64 d to the power 4, and the value of C will be same as, that is the distance C will be equal to same as d by 2. So maximum stress will be produced either at this point or will be at this point, that is along the z-axis. Whereas in the rectangular post, this one is the centroid here, and again this time this axis is our y-axis, and the moment is taking place about the y-axis, and this moment is again a clockwise moment. And if you take the perpendicular distance here, so this one is the same as the force is shifted equal to P, and we have eccentricity this time is same as the previous value, that equal to d by 2. So eccentricity is same as d by 2. Whereas the centroid we can locate here, and we can system fix up here. Horizontal axis is Z, vertical axis is Y. So this time the moment of inertia I about Y is parallel distance multiplied by perpendicular distance cube divided by 12. As far as the y-axis is considered, we have parallel distance is same as equal to the distance B. Perpendicular to y-axis is distance D. So we have parallel distance is B, perpendicular distance is D cube divided by 12. So these are the points that will get you confused. So remember the definition of IY: parallel distance to Y multiplied by perpendicular distance to the Y divided by 12 in the case of rectangular section. And the maximum stress will occur at this point or at this point, same as the circular section. So in this case the value of C you have to take as d by 2. So value of C1, value of IY1, value of IY2, value of C2 are known to us. So let's calculate here the maximum tensile stress for circular post, that is A, will be equal to minus P by A plus V of M multiplied by C1 divided by I1. That is basically IY1. This one is M1. M1 is same as here P into E. So we have minus P. This time we have circular cross section. So we have area is equal to pi by 4. In that case 4 will shift in numerator, and in denominator we have pi d square plus we have M1. M1 is same as P multiplied by E. So we have force P, and distance E is same as d by 2. That is the eccentricity. C1 distance also equal to d by 2. So we have d by 2 and is divided by IY1. IY1 is pi by 64. So we have pi divided by 64 multiplied by d to the power 4. So this 2 and 2 is 4, and this one is 64. So 16 will come in numerator. So we have minus 4 times of p divided by pi d square plus this maximum value will be equal to 16 times p divided by pi into d square, because d square is cancelled from d4. So we have d square. So 16 and minus 4, that will be equal to 12 times of p divided by pi into d square. Same computation we have to do for rectangular section now, and then we'll select our choice. So we'll do the calculation for rectangular post, that is b. So we have minus p by a, and we have value of m is same as equal to m2, and m2 here is again p multiplied by e multiplied by c. So we have c2 divided by iy2. Remember iy2, moment of inertia. Moment will take place here about the y-axis, not as per the z-axis. So that is why we have taken here b. B is what? Parallel to y-axis, and d is perpendicular to y-axis. Okay, this one is a rectangular section. We have area is equal to b multiplied by d. So we have minus p divided by area is b multiplied by d plus m2. M2 is same as p multiplied by e. So we have p, value of e is equal to d divided by 2. Again C2, this time C2 is also equal to d by 2. That is, this fiber will experience the maximum tensile or compressive, or this fiber which are distance from the centroid is equal to d by 2. So again multiplied by d and divided by 2 divided by iy2, that equal to bd cube by 12. So we have b into d cube, and 12 will shift in numerator. So this one is a d square and this one is d cube. It means that denominator is bd. We have 12 and 4. It means that we have 3 times. So we have minus p upon bd plus we have 12 divided by 4 equal to 3 times of p. D square is cancelled, and in the denominator we left here with bd. So maximum tensile stress in the case of b will be equal to 2 times of p divided by bd. And the maximum tensile stress in the case of circular post is 12 times of p by pi d square. So maximum tensile stress for circular post come out to be 12p by pi d square. For rectangular post is come out to be 2 times of p bd. He says that the maximum tensile stress in both the post will be same. Then you have to find out the relation between the width and the diameter d. So as per the given condition here, the maximum tensile stress in the circular post and the rectangular post is same. It means that we have 2 times of p divided by bd is same as equal to 12 times of p divided by pi into d square. So clearly here 2 is get cancelled. This is 2, so we are left here with 6, and one of the d is cancelled, so only d is left here. Finally we'll cross multiply here. We have 6 times of b, so we have 6 times of b is equal to pi into d. That is, we have width is equal to pi by 6 multiplied by depth d. Pi by 6 multiplied by depth d. Our choice B is correct choice. The video you are watching is from the app, which is the More Class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.